Okay. Yes. So I'm actually recording the talk right now, so that I will be able to post the talk for thousands of YouTube downloads, but also for the next generation of small students who come, I can just give them this to look at. I might be able to stop it. Yeah. Well, the real thing is I want to just film the slides. And so I will post the slides with the audio. Yes.
Okay, so our next speaker is SJMiller, who will talk about optimal test functions for n-level densities and applications to simplifying functions.
So thank you. It is always fun to come to this conference. This is one of 3 non-negotiable dates I have in my family where I have permission to always come to this conference. And so it's wonderful, and I've been able to bring many students here over the years. It's the first conference for many of them, and it's extremely friendly. Unfortunately, I'm not bringing Charlie Devlin, who is responsible for most of the work. And so instead, he is doing things like classes and exams and homework. So he's left me to talk about the actual work that was done. So what I want to do is I want to talk about the problem. I want to talk roughly about the reason why we care about this and what roughly the techniques are. The details of the techniques is actually not a number theory talk, it's actually a functional analysis talk. So rather than going through many, many slides of functional analysis, which for those of you who want to see, you can just start reading over here and just go from that point onward, you are welcome to look at all of those. But I want to concentrate instead on the big picture. I also want to just briefly give a shout out to the Journal of Number Theory, where I am one of the managing editors. We are able to provide support both to graduate students, to young postdocs, to young faculty, as well as to number theory conferences. So if any of you are organizing a conference in the future and would like some funds, we are happy to work with you. I would say more, but since this is being recorded, that stuff is better said later. You can just shoot me an email, sjm1@williams. Okay, so I want to first review L functions. One of the nice things about having Andy schedule me later in the day is a lot of the stuff has already been done, so I can go very quickly. The main application today is bounding, average rank, or high vanishing in families. And the idea of proof is basically to use tools from functional analysis to study the problem and to somehow reduce the dimension of what we're looking at to something that's a little bit simpler. So as time permits, I will give some of the explicit bounds at the end. I have not optimized this. I am hoping that time will not permit. As the order of vanishing increases, the bounds get better, but they start off quite bad. And so building on Andrew, who built on the words of wisdom from the dean, I thought I would modify my talk and talk about some of the worst results I've ever proved, which I don't think anybody ever called brilliant. The first was approximately at most 250% of cuspal new forms vanished to order 2 or more. I actually got this into Compositio. The second one is there are at least log x primes at most x. And what I like about the second one is one of the ingredients, that paper actually uses the prime number theorem to get something that I have to deal with. Now, both of these papers have more content to it than what would look like from over here. And the first one, that approximately 250% of cuspal new forms vanish to order 2 or more. Yes, that result sucks. But as you go further to vanish of order 4 or more, or 6 or more, the results start getting better. And the further you go, the better the results get. But initially, the results are much easier to prove than the argument that I will give later. All right, so quick review of L functions. All right, thank you. Riemann zeta function, we all know it has a functional equation. Proof pending, all the non-trivial zeros have real part 1/2. If you would like, the Journal of Number Theory typically gets 1 or 2 proofs of this each week. If any of you would like to look at one of these proofs, I am happy to give them to you. And I can even compensate you for looking at these proofs. We will always assume that there's an Euler product, that there's a meromorphic continuation, that there's a functional equation. For the most part, I'm not going to talk about number theory objects, but it's just good to know roughly what is the class of things we're looking at. So the main problem is going to come from looking at things in random matrix theory. So there's 2 different types of matrix ensembles you can look at. The physicists started off by looking in the 1950s at real symmetric complex Hermitian matrices. These were nice matrices where you chose the entries independent, identically distributed random variables. Depending on physical symmetry, you would often be able to say that the matrix is a representation of a transformation. If you change your basis, it's got to be the same transformation. So I want a probability distribution that's invariant under a unitary change of coordinate system. That's where the Gaussian comes in, the Gaussian unitary ensemble, Gaussian orthogonal ensemble. It comes from this change of basis. The number theorist said, yeah, that's nice, but that's not a natural choice. And so the number theory really developed from classical compact groups where through Haar measure, you have a natural way of choosing what you mean by randomness. So we want to study the distribution of normalized eigenvalues for different ensembles of matrices, or you can look at equivalent problems. And one of the wonderful connections is that if you look at many different systems, zeros of L functions, eigenvalues of heavy nuclei, eigenvalues of matrix ensembles, you see the same type of behavior. The calculations are often very different from one to the other. But the nice thing is because we can do the random matrix theory calculations, we have some idea of what to expect on the number theory side. And so as I've remarked, the Riemann hypothesis allows us to say all the zeros have real part 1/2. That means we can order them going up along the line. And then there's a lot of different statistics you can look at. So the statistic I want to spend my time on is the one-level density, or more generally, the n-level density. So what we do is we take a nice Schwartz function phi, and we look at a scaled set of zeros. So we normalize the zeros so they have mean spacing 1 near the central point. And what's nice about this is for a lot of L functions, think elliptic curves, the action is happening at the central point. And this is going to be a statistic that will capture what's going on. If you want to look at spacings between zeros, this is the Montgomery-Odlyzko law. This is looking at n-level correlations. If you know all the n-level correlations, you know the spacings between zeros. If you care about spacings between zeros, one L function gives you infinitely many zeros to look at. What's going on near the central point, that's going to be a finite amount of noise, and in the limit, it's not going to contribute. But if you care about what's going on at the central point, these statistics will not be successful. What was fascinating is Katz and Sonak found that the modeling that had been done to look at zeros of L functions by comparing them to eigenvalues of complex Hermitian matrices, there was a terrific agreement, but other matrix ensembles would also give the same result for spacings far away from the central point. If you want to look at what's going on near the central point, it turns out that the classical compact groups and the eigenvalues near 1 do a phenomenal job, and different families of L functions have different behavior. So this is the quantity we want to study. It's going to capture what's going on near the central point, and because phi has rapid decay, it's only the zeros that are close to the central point that are going to really matter. And the idea is that if we can calculate this, we should have some idea of what's going on near the central point. In an ideal world, and it's not my advisor's fault they tried, you would be able to do this calculation with a Dirac delta functional and just shoot in what's going on at the central point. We can't do that. We can only do these calculations if the Fourier transform of phi is suitably restricted. And so because we can't shoot in a Dirac delta functional, we can't use this to prove things like the Birch-Swinnerton-Dyer conjecture. We can't get an exact understanding of what's going on at the central point. So the goal is, depending on the class of functions you can do this calculation for, what does that tell you about the behavior of the L function near the central point? The larger the support, the more you can understand. I know that this is a bilingual conference. My second language is not French, it's actually physics. I was trained by a nuclear physicist who was fed up with the paucity of data in nuclear physics, where 1,000 data points after 2 years of work is terrific. And so he actually taught me number theory, because he was migrating over to looking at the Riemann Zeta function. And the analog is, in number theory, we study zeros. In nuclear physics, they would study the energy levels. In number theory, we shoot a Schwartz test function and see what happens. In nuclear physics, they shoot a neutron and see what happens. In number theory, we can only do things with a suitable support. In nuclear physics, that turns out to be the energy level of the neutrons that you can shoot in. And so the goal is, what's the largest class where we can actually do these calculations? So if I fix a specific L function, it's got finitely many zeros in a small localized neighborhood, rescaled near the central point. Whatever the zeros are, that's what they are. In several talks today, I'm not sure what room you're in, but almost surely you've heard a talk where people said we need to average over like objects in order to be able to do anything meaningful. And so what we'll do is we'll average over a family of L functions. When I was a grad student, there was not yet a good, rigorous definition of family. I'm not sure if we have one yet. It's basically that you know it when you see it. Cuspal new forms, that's a family. Dirichlet L functions, that's a family. Symmetric square lifts, that's a family. So we look at some family of L functions, and then for each one we calculate the statistic, and then we normalize by the number of forms in the family. And then the hope is that in the limit that this will converge to something nice, where W is some distribution depending on the family, and different families might have different limits. So the Katz-Sarnak philosophy is this W is coming from classical compact groups, that you give me a family of L functions, there's a corresponding family of matrices that have similar behavior. And the tie is through looking at function field examples and monodromy groups there. And so just to have some explicit statements, here's what the forms look like for the one-level densities. So you have nice sines, Dirac delta functions, nothing too bad, but to actually work with some of the stuff is going to become quite painful. And we don't want to look at just one, we're going to look at n later, which is going to make things a bit worse. So there's a lot of quantities you can look at. The first is just the average rank. And there's been a lot of discussion, especially for families of elliptic curves, is what can you say about the average rank in a family? So if we choose our function to be non-negative and even, well, what's nice is if it's non-negative and even, there you go back, oops. One more slide, I think. Yes, when we look at something like this, if everything is non-negative and even, all I have to do is drop every term but the zeros at the central point, and I've dropped a positive amount, so I get an upper bound. So if I do that, I can trivially get the following as an upper bound. And you can do other things. If you care about high vanishing at the central point, you can do this as well. And you can use this to get results about how often do forms vanish to a given order at the central point. And of course, the smaller results you can get for the quantity on the right-hand side, the better your results. So the game is, given your support restrictions, given that you can calculate number theory for test functions whose Fourier transform lives between minus sigma and sigma, what's the smallest you can make the right-hand side? The other approach you can do is to look at not just the one level, but to look at the n level. And there's multiple things you can look at depending on where you want to pay the price for combinatorics. You have to pay it somewhere. The n-level density that Katz and Sarnak looked at is they sum over distinct zeros where each index is not plus or minus another. Another thing you could do is say, screw this, let's just sum over everything. And instead of looking at the n-level densities, you'd be looking at the nth-centered moment or the nth moments. And you can really go back and forth between either one, depending on how you want to do the calculations and what do you want it to match to. And so you now get some kind of weighted bound. It's a little bit annoying because since the J's are distinct in the indices, it's not just taking, if it vanishes to order 5, phi of 0 to the 5th, but you can calculate what that is. And you now get a bound in terms of these integrals of a little more involved quantities. And then the goal is to minimize the right-hand side and get the smallest thing possible. So I only have until 40 past, so I'm doing pretty good about being able to avoid the technical details. Excellent. All right. And so in my thesis, I mentioned one of my worst results ever. It was the following thing, which I then extended a little bit with Chris Hughes, is that if you look at the little n level density, you can show that the probability of having at least r zeros at the central point is at most some constant depending on n times r to the minus n. So if you fix n and let r go to infinity, you actually get better decay than looking at the one level density. The problem is the constant Cn grows, and that's why at first you get these stupid results such as at most 250% of the forms vanish, which you could have proved, as I've said, more easily. Right. So to see what the ingredients are, here are the n-level weights for the classical compact groups. It basically involves determinants of matrices involving signs. And then the philosophy is to basically be very careful when you're a graduate student and choose good advisors. And so I did an excellent job. I worked with two, Henrik and Peter, as well as their postdoc who kept migrating back and forth between Princeton and Rutgers. And so in their paper where they looked at the one level density, one of the results they had was they had to look at their test function hitting against a Bessel function being multiplied by a bunch of Riemann sums and summing over a variety of things. And they calculated this one level quantity. And it's beautiful how they were able to simplify this and get a beautiful expression like this. rather than going through all the details of how we're trying to simplify the functional analysis problem, I thought I would show you how to simplify the higher level versions of the quantity that they looked at. They looked at the 1-level density, what you would do for the 2-level density, and then just say something similar can be done in the functional analysis side. Talk to me later over a drink if you really want to see the details. So this is the 2-level quantity that emerges. And so you have a Bessel function, now you have a product of 2 variables, and you have to integrate over all of this. So step 1 is to basically say, let me try to generalize their theorem directly. Or a different approach is to say, let me see if I can make this look like what they already did, and then say, by the work of my advisors, I'm done. And so changing variables, the natural choice, you let u2 be x1 times x2, let u1 equal x1. The only other possibility is to let u1 be x1 times x2, but I don't know why you choose that notation. If you do it like this, the Jacobian is beautiful. It's a 1 over u1. When all the pieces come together, it looks almost like what we had before. We've got a log of u2 over u1, a log of u1. We've got a u1 over here. If I now do another change of variables, if I let w equal the log of u1 divided by the log of r, then I get the log, I get phi hat w1, phi hat log u2 over log r minus w1. This looks like a convolution. And so it is. You can actually say by the support restrictions, the functions vanish if the support is less than minus sigma. So I can actually extend the integrals up to infinity. It's now like I have a new function, C2, which is related to the others. I plug that in. It's now the same 1-level calculation that they looked at before. And now I can just use their result directly. The work that has to be done now is the Katsonic determinant formula was expecting a 2-level calculation, and we've cheated. We've made it a 1-level calculation. So now you have to do some combinatorics to show that it agrees. All right, so just outline of the main results. But I wasn't sure if anybody would notice. So the main idea is we're looking at a n-level product now. So why not try to do the same thing as before? Let's assume our test function is a product of n one-variable functions, which is typically done with a little bit of work. You can say, yeah, it's not as general as the most, your phi of x1 through xn, but it's close enough. And for the most part in the literature, nobody really cares. And then you choose n minus 1 of the factors. Maybe you choose them to be what was optimal in 1 dimension. And then that leaves you 1 form to fix and try to optimize. And then you try to apply the same tools and techniques you did in the 1 level to deal with that last one. And then maybe you keep iterating things back and forth and say, well, if this one is better, should I have changed games like that? You start with the 2 level where there aren't as many balls in motion and argue along these lines. So just briefly showing what the 1 level case is, there are 2 steps. The first is to reduce to a different optimization problem than was originally given, and then use functional analysis to solve the related problem. So, briefly, we have our integral of phi times our weight divided by phi of 0. By using Poincaré, we can rewrite it as follows. And then there's a bunch of theorems at our disposal that say, well, if you're a minimizer, then you have to have a certain form. And so this is in the appendix to ILS's paper by, I think, Jeff Vanderkam. Okay, good. And so, we can follow his work. He only calculated things, I believe, up to minus 2,2, because on the number theory side, the results could only be proven up to minus 2,2. And so the results were pushed as far as possible on the functional analysis because number theory wasn't even close to needing a better result to find an optimal test function. The other thing which is interesting is there are certain functions which are much simpler to use and do almost as good of a job. So if you don't want to go through the whole optimization problem, you can still get pretty good results without doing too much work. And so there's a whole slew of results that show what your forms have to look like. And when you just go through the analysis, you have some functional analysis, some more manipulations. There's no period here, so it has to continue. So you keep doing some more slides and some more work. And then you get a new related problem. And then you just minimize that one. And then there's some games you can say, well, if I want to push it further, how far can I keep pushing, going on and on and on? I'm just going through it like this because now if you hit pause on the YouTube video, which I know you'll all go to later today, you could actually see all the slides without just clicking on the slides that are off to the side. So for the n-level case, we basically just choose phi2 through phi n, integrate over those n-1 choices, because now they're fixed functions and we can do the integration. And now we have a one-dimensional problem, try to optimize that, and then lather, rinse, repeat, keep going back and forth. So just, going through things at beyond warp speed. Okay, and then we have a little bit of a follow-up from the conversation we had at the end of the last talk about if we were looking at n not square free, we had a lot of trouble with the root numbers in terms of splitting by sign of the families. It's wonderful when you're looking at families of cuspal new forms that if the level n is square free, you can write down the root number, the sign of the functional equation, in terms of the Fourier coefficient at the level. And that allows you to split everything by just doing more sums, and you can use the Peterson formula. So we can actually get somewhat decent results right now in terms of the probability of having, I think, rank 0, rank 1, if we're looking at some of these even odd families. This is not connecting to number theory right now. This is just saying what we're able to do. To have good connections with number theory, it comes down to how far can you calculate the n-level densities. Typically, you can get up to 1 over n minus 1 without too much trouble for the 2-level density for families of cuspal new forms. With a little bit more work, you can go a little bit further, but there are real obstructions that emerge. That is the topic of a future talk. So, thank you. I can take off the hat now because my son's team won their baseball game 4-2 where I'm a coach. Wait, you're gonna, I'm gonna just turn it back to you, but okay.
Wait, I can decide.
No, please.
So we experimented with this function product.
So the only test functions we've looked at are products.
Yeah, and technically I think the group forms and the group. If you do it with large sufficient value, once you get it for product, you can get as identity. I'm not saying that would be really practical.
Right.
You can reduce
Well, I think, I mean, I've heard some people say that there's a slight loss in information if you are always requiring your functions to be products, just because of how the support restrictions work. Right.
For identity, for the correlation with function which is not just
right. I mean,
you can also answer just do it, and probably will be having a head. Not intelligent way of doing, but you can.
Right. This is actually right. This is actually one of the reasons why I like looking at the n-centered moments rather than the n-level densities, because then you just choose one function and you work with that. And then as long as I have time for a technical question, going back to what you were saying, yes. Right, here it is. So when you look at the n-level density, what I've done here is I've normalized each 0 by the local factor, by the log of the conductor of that form. If you look at just the 1-level density, this actually makes the calculation a little bit harder. And if you just care about the 1 level, it's actually better to normalize by the average log conductor. But as soon as you have a 2-level or higher, you end up having cross terms when you use the explicit formula, and you are stuck no matter what. And so for families of elliptic curves, there's a tremendous amount of sieving that has to be done no matter what. And so as long as you have to do it, you might as well have each form normalized correctly. But one nice approach is if you are looking at the n-centered moments, then you don't have all of this nasty product, and you can use a global rescaling rather than local rescaling. Right. Right, unless you're doing things like cuspal new forms or Dirichlet functions. For elliptic curves, it's terrible. Right.
What can you say about Dirichlet functions with your optimization?
Well, the nice thing about Dirichlet functions is the conductors are either constant if you fix the level, or they're monotonically increasing. What I'm saying is, as long as the conductors are constant or monotone in your family, the technical obstructions vanish. And so the problem with elliptic curves is, even if the conductors are almost constant, and differ only by, say the size, n to the fourth, but maybe it goes from n to the fourth to 2 times n to the fourth, that fluctuation is enough to have the calculations all over the place. It comes down to you have a finite interval, and if the conductors are monotone, you traverse the interval at most once and you can bound it. If the conductors can vary, then you could actually traverse the interval on the order of n times, and you have a tremendously large term to deal with. I feel like I'm finally defending my thesis.
Any other questions? Yes.